now it's time to introduce the next speaker, the last speaker of the day, who is Professor Onno Bokhove. I hope I pronounced that okay. So just a brief, I will try to do it better this time. Also, it's very hard to see, but let's see. Professor Onno, he's the chair in geophysical fluid dynamics at the University of Leeds, and he's also a member of the Leeds Institute for Fluid Dynamics. His research expertise spans geophysical fluid dynamics, computational fluid dynamics, and mathematical modeling of environmental and industrial flows. So he's made significant contributions to areas such as flood mitigation strategies, wave energy mathematics and design, and development of discontinuous graphically finite element methods, and over 100 articles of that. He at Leeds, he also serves as the industry group leader for the Institute of Fluid Dynamics. I hope I got that right. He also teaches in those areas, advanced postgraduate modules. And lastly, his interdisciplinary approach combines mathematical rigor with practical applications, addressing critical issues in environmental fluid dynamics and sustainable energy solutions, which is something we probably see about today. So without further ado, the floor is yours. Thank you so much for thank you.
Well, thank you all for being here, and thank you all online for being here. I'm bowing at you. Thank you to the organizers for inviting me. I'm Onno Bokhove. At all, that's for this work 9 people, so I can't be 9 co-authors, so I can't beat. Rebecca has to the toilet. 140 co-authors. I did a quick count. I came to about 60 co-authors. So I'm going to talk about flooding, in particular 2 aspects of visualization in flooding, and it's really outreach and policy. So that's why you see floods. One, you might recognize me on the left. So I led for a couple of years EPSSC network, which was called Maths for Seas. It brought together applied mathematicians, statisticians, and people, professionals who forecast things, extreme events, the Met Office, Environment Agency, and the Environment Agency posed and stated 2 challenges during that network. And the first one was, how can we visualize return periods for extreme events, in particular flooding and rainfall, in a fluid dynamical setup? So they didn't want a simulation, so as opposed to doing that in a simulation. And this challenge was posed because some people think that these events of a certain magnitude are regularly spaced. So I recall an interview in 2019, BBC. It was interviewing a business owner from Fish Lake, that's just north of Sheffield. And this was a 1 in 100-year flood, and she had heard, and it affected her business. But she said, the other 1 in 100-year flood was in 2007, so I thought I was safe. Yeah. So I was luckily alone in the room, because I said, you should see Metropolis, because the answer to the challenge is the visualization of return periods in the Metropolis flood investigator. And I will describe the flood investigator. The second challenge wasn't so much posed as it was a statement, a remark, which I somehow picked up in my brain. One person, so it doesn't reflect the Environment Agency, one person from the Environment Agency, which was in the network, said, well, you mathematicians, you solve these partial differential equations and ordinary differential equations, existence and uniqueness sometimes. That's so difficult. Can you not do something which is comprehensible to decision makers? Well, I will also give an answer. the only answer to that challenge, and that will be a graphical cost effectiveness tool to visualize flood mitigation scenarios. And that one had kind of two pieces of motivation. One, this challenge, and then an actual flood. So let's go to the first challenge. So this is what then happens in my brain. So we want a fluid dynamical setup. At least that's what the Environment Agency wanted, and I like that. So what are the basic ideas and ingredients? How does it morph in one's head? Well, oops, there is a, is it a pointer? It doesn't really matter. There is a concept. Let there be a conceptual river catchment. Conceptual, because I'm a mathematician. It doesn't need to be a miniaturization. So I need a river, because I'm interested in river flow, a floodplain, one-sided for space reasons, a porous moor, so that you can have some delay of the rainfall into the river, and then a reservoir, and if the reservoir is full, it will instantaneously flow in the river, so it's kind of like urban hard surface. And then downstream somewhere there is a city, conceptual city. Now instead of a 1 in 100-year event in 1,000 square kilometer catchment, you need to reduce space and time scales. I always say, I don't want you, when you look at the setup, to wait for 100 years on average, because then we've all turned to dust, right? So I need to shrink the spatial and temporal scales. So in Metropolis, there's no annual, there are no years, there are only days, Metropolis days. So it's a new SI unit WD, right? There it is. Of length at the time I assigned it, unknown length TD, right? Say seconds, minutes, you name it. Now I said, let it rain in 2 locations only. In the moor, which I've just introduced, in the reservoir, so that's 2, in both places, and the 4th possibility is no rain, right? I want to limit the options. Now it can rain a certain 4 fractions of this Metropolis day. So F1, F2, F3, and F4. And they lie between 0 and 1, and I've ordered them. So that means that there are 4 or more outcomes, because if they're a factor of 2 of each other, then if they're not a factor of 2 of each other, then you can actually have more and more outcomes. And then for us, this is just some silliness, but for when F1 is 0.1, so 10% of the time I call the rain rate a unit R0. It's just the definition if you wish. Then I took a length of river in my mind, which was somewhere between 1 and 5 meters, and I didn't want things to be too small, so my river width is a few centimeters, and depth as well. Those I kind of didn't consider unknowns, right? So then the remaining design unknowns to see if anything was feasible at all are the length of the day, TD, and this rainfall unit R0, right? Could I do something which was manageable? So this is
conceptual river perfectly straight.
Well, that's an interesting question. I didn't set this up. Oh, quite too bad that now. So, so this is then what I said in the map. I have the blocked blue, white. That's the main river channel on the one side to the dashed line. The one side is slightly sloped. A floodplain. I chose the 1 in 100 slope of the river, place the porous moor here, the reservoir here, later I put it here, and then here I have a city which can flood. And there is also a canal because it was inspired by the Boxing Day floods of 2015, and Leeds has a Leeds-Liverpool canal, right? In a later version, I skipped that. In my first design, it was all straight. 1 meter, but I made a silly mistake in the Manning coefficient, so I needed more length, and wanted to fit it in 1.2 meter by 1.2 meter setup, so I needed to wind it around. That's how life goes sometimes. So how is rainfall put into Metropolis? What I've done here, the weather machine. How do I determine these 4 times 4 outcomes, right? 4 for location, 4 for rainfall. Or actually, there are rather 13 outcomes. You should have remarked, because if there is no rain, F1, F2, F3, and F4 don't matter, right? So there are really 13 outcomes. So usually I do these things on some train ride. I should be put on more train rides because on the back of the envelope, I made up a discrete distribution. And I felt it should have a tail, a discrete tail. So this is then leading to the first setup with the first carved routed piece of wood. It's slanted. You put the ball in here and then you look where the ball goes. And then you assume that the wood is perfect. It's not, but it's roughly perfect. So there are 4, if you want to count this one, 5 rows. So the probability that it goes through here, the ball, right, is 1, and then it gets to a split. It's half-half. Then I cut this split to get the tail or the discrete tail. So that stays half. Half becomes a quarter. You get 3/4, 1/4. And 3/4 becomes 3/8. 3/8 combines with 1/8 to half. This becomes 1/8. And then I had enough, right? It was out of breadth of paper in the tray. And I didn't want to make it too complicated because it was meant to be understandable to everyone. So then I finally ended up with 4 channels, my 4 outcomes. Probability 3/16, 7/16, 5/16, 1/16. Well, I'm not a statistician, so I kept it really simple, not only for that reason, but because it needed to be comprehensible. So this is a modified Galton board. Usually Galton board is symmetric, and then if you have infinite rows, you get the normal distribution. So then I needed 2, I just copied them. One is used on the left for location. Here are the balls. And I assigned 1, 2, 4, and 9 seconds to the 4 channels. And in black are optical sensors, which then notice or record which channel the ball falls, and that gives then a corresponding reaction in the setup. And on the right, here is a location. So either the reservoir, in the Moran reservoir, the more or no rain. And no rain is 1/16, right? So that was a rare event. We are in the UK, so it doesn't, it's, so that's what I did. So if
you can go back, so the thing that looks like a train set in the back, that's actually the river, right? This green thing there in the photograph, what is this?
Can you just wait?
Yeah.
Yes, it is. So if we now, so we basically have the total probability matrix is the product of the probabilities of the location, discrete probability times the probabilities of the duration. So I have the reservoir, Q1, both Q2, more Q3, no rain, Q4, and likewise 1, 2, 4, and 9 seconds. So then it's a matter of choice. And the bottom ones are the blue ones, and they add up to 16 because I've taken out the base 16 squared to 256. And I need to do it in a simple way because it's explained to everyone, right? Not only to mathematicians. So that's in the game. And then the question is, which one do you choose? So in the first session, Wetropolis, which I call in my head Wetropolis 1, right? There's like a king, Wetropolis, King James first. There is a Wetropolis 1. I chose this one. So 9 seconds of rain. And in both places, that's my most extreme event in this setup. Right? Because it's the most amount of rain in both places, right? So that gives you actually 18 units, because I'd say 1 unit, well, actually I will later say 1 unit is 1 second. Now I got the question in Korea, is it unusual, is it usual for a mathematician to make such fluid dynamical devices? They felt it was very peculiar that the mathematician was doing this. So I learned some Korean this year, and I said, well, I don't know. Okay. Then as it happens, the Galton board, invented by Sir Francis Galton, was a British polymath and a mathematician. Now it's important to realize that the innovation of Wetropolis lies in the coupling between this weather or rain machine and with its skew Galton boards and the conceptual river catchments. Loads of people use Google, they're played with Lego, they have made a river catchment, they throw water at this, preferably as much as possible, but that's completely unrealistic relative to extreme events in the real world. So the innovation is the weather machine. Now, I'm not going to show it, but underlying Wetropolis is a mathematical and numerical design model, partial differential equations, and ordinary differential equations, and diagnostic relationships, linking all the components I had sketched in this map. I basically, before I went to the person I usually design with, which is the designer and artist about spheres, I first made a calculation with then the slight minor coefficient mistake. But that was easily fixed after I got a lot of laughter from the designer that the mathematician had made a mistake. Oh well, but it was easy. It was easy to fix. I'm not highlighting this because it's a page full of equations. None of them are particularly complicated, but piecing them together, you need to do a bit of thinking. That for me, because that's what I usually do, that was the easy part. And in some sense, it's not the innovative part. The innovative part is the combination with the brain machine. So this question, is it usual for a mathematician to propose fluid dynamical devices, came when I was in Dijon in Korea last August, the Korean Advanced Institute of Science and Technology. Now, people who know me, Wetropolis is a member in a series of fluid dynamical popularization devices I've made over the last 20 years. And they're often based, not always, on mathematical and numerical design models. Now, I did not solve the Navier-Stokes equations for this. One should, to be really precise, right? But it's important to realize that for a design model, if you're interested in making a fluid dynamical design, you don't need that precision. And you actually shouldn't do it because you waste your time. So a design model, I think it's important to stress, is not a suitable or detailed predictive model. I just want to stress that. Quick and dirty, as long as you get what you want. That's the message. Because otherwise you get hung up. So the design model with HI optimization suggested a Wetropolis day length of 10 seconds, so that's the one Wetropolis day, and a rainfall rate of 0.18 liters per Wetropolis day. So once I saw that, you Google and see which pumps can do that. Well, just aquarium pumps, which you can buy around the corner, right? So I knew I was in business. I could deal with it without having any fancy stuff. HI optimization is just human intelligence, right? That was me in this case. So 10 seconds, that's the Wetropolis day, determined by design. And I did that by saying, well, I want no or minor flooding for this amount of units, so 0, 1, 2, 4, and 8 to 9 units in the model, when I choose that 1, 2, 4, and 9 seconds. And of course, now you see why there are not 4 outcomes for the rainfall unit, because one unit when it is in both places gives you 2. 2 seconds of rain in both places gives you 4 units. And likewise, 4 units in both Moore and Reservoir gives you 8 units. The 9 stays the 9, but the extremum comes when there is rain in both places, the Moore and Reservoir, and that gives you 18 units. And I made the design that should say, then I get the flooding. Now, what's the return period? You can debate here, so I have to look at Rebecca, whether this, if for rain, it's the daily exceedance probability, because I only have a day in Wetropolis, but I kind of took the daily event probability, but in this discrete setup, that's the same. At least that's what I think. So what is the return period? Well, we would like, when you have a deterrent, when you want an extreme event in n days of 10 seconds, then you have n-1 days with probability 1 minus PE, and 1 minus PE is my 7/256, and then times 1 PE. And then you take this as a first year exercise, you basically use a geometric distribution, and when you take the expectation, you get that, of course, it scales with the time period of time of day over the probability, and that's about 6 minutes. So in the setup, that means that people sometimes have to wait 1 minute and then sometimes 12, right? And that's what it is. That was designed. There needed to be enough annoyance. Where is this extreme event? Because otherwise it's not extreme. But it needed to be short enough that they didn't walk away. right? So that's the game. That's the game, the task to play. The standard deviation, Dan and Jason said it has to be. I've never calculated it. The thing worked, right? At your event, right, 2 years ago, Jochen, they said, well, it must be the standard deviation around the same time, otherwise you would never see it, right? So, and that actually turns out if you take the expectation, oh, where's my big, then it's about a little bit shorter than 6 minutes. So it's 1 minus PE, the square root of 1 minus PE times TD. Now, the Boxing Day flood in Leeds in 2015 occurred because there were 2 days, 48 hours of extreme rainfall. Well, I can look at that in Metropolis. I can take 2 consecutive days with a Metropolis exceedance probability web, right? Which is the square of 7 over P squared. And that's about 3 hours and 43, 3 hours and 43 minutes, which is rather long, so I haven't seen it that often. Actually, as it happens, the sign won, the day we designed it and everything worked. I saw it and I filmed it. It was like, how is it possible? But it was true. And I've seen it more often. So it was just quite surprising. Now, you would think, oh, my cursor is again going, that it's 1 over PE squared. But it turns out it follows a geometric distribution of order K. And our K is 2. And I was surprised, this is rather late. I thought it would be around 1900, right? But this is rather late. The return period scales like this, so it scales like 1 over PK, but there are some prefactors, but for this small value, these you can ignore them, right? So it's roughly 1 over, and the same for the 3-day event and the 4-day consecutive rainfall event, and etc. And here you also have the standard deviation. So it's slightly longer due to these corrections, but so be it. That suggested the V design, which really came about when I was at the Isaac Newton Institute event which Jochen organized in Reading 2 years ago, namely take another value of PE to bring things, to have more variety in the model. So I took the probability 7 over 16 squared. I will show you the probability matrix again. And then the return periods for the different consecutive rainfall events are 52 seconds. That's a flood. About 5 minutes. That's a super flood. And then this one, which is very rare, a mega flood. And that just makes the visualization more interesting. But that's the game, right? I need to visualize it for the public. So I did that. So this is the same probability matrix. So I moved that. I didn't make it 9 seconds for technical reasons. I swapped the 2 and the 9 seconds and made it 9 seconds, 7 seconds. And then this one gives you the extreme event when you can play with that. So that's what I did. And I could do that with the same setup because it's all linked to Arduino programming. So that's the current case. Sir, you are on. So now you sit down. Jochen said, why didn't you bring it? And I said, why didn't you ask me? But this is second best. Ready? You. I'm not done yet. You're back to the slide. No, you're doing it perfectly. It was made about 8 weeks ago. I had a bit of a, well, fight is a big word, but let's use it anyway. With the movie maker to put in the blackboard, and you noticed, and this was better in the second round, 7/16 squared is easily more to easily explain is 1/5 than 7/256. So for explaining it to the public, it's much better. 7/256 is already too complicated. So that's where the 1 and 5, you see it's not quite matching. It's much easier to explain. And I hadn't realized that. So I foolishly decided at your event to, I thought that's it. That's what I should do. So really, that's my answer to the, or our answer to the, oh, thank me. There we go. So a few remarks. So I really focused on rainfall. The actual probability of flooding in the city is not as simple as the rainfall distribution, because with my matrix, I've made a multivariate distribution because it rains in 2 locations, right? So it arrives at the city in a more complicated way, also because I have the Morwich buffer. And I haven't done anything on that. So just to be determined, well, we did a little bit, but not much, because it was a demo tool, not yet a research tool. Then in 2016, I was in Oxford, I gave a presentation on Metropolis, and I got the question, where's climate change? So I smiled, but I was raging. Do I need to have climate change? It took me 1 second. I said, well, I add an extra pump, which is in sync with more. And then you have a change point analysis, right? If I don't tell you when. So that one is put into the model. It didn't get into the film, but that's put it so I'm done with it. And in 2018, with Ryson, I get the question, where droughts? Again, I was smiling with radiant. Internally, I know how to do it, but I haven't made it because the visualization of nothing happening is much more difficult. So I can do it. You can ask me later. It adds, because I only had half a smaller pump, about 20% more rain. The Galton board, when it's symmetric, so the standard one gives you the normal distribution if you have an infinite amount of rows. Now, if I keep adding rows and I don't cut off blocks, I'll again get a normal distribution because the one cut at row 2 doesn't do anything. But I don't know, this must be done by statisticians, but what happens if you now and then block one? Can you actually reproduce other continuous distribution? That's more of a game, but I played with it a little bit because it's not that important. The board has sometimes problems that the ball hangs, and how is this possible? It hangs exactly on a tip, and it's absolutely infuriating. Well, some randomness. So if you would make it computerized, but with a LED board visualizing what's happening and maybe adding the sound, because it makes a heck of a sound, the ball is falling through, then you have more variability, and you can also put in different distributions, but this is just fixed to 1, right? When you mill it, that's just the way it is. So there was a suggestion by Roman Furse from the CDT who helped demonstrating it. So the movie leads to the second part, so the second challenge. So that's the challenge, how can you visualize flood mitigation scenarios for decision makers? And it was also triggered because I called the flood activation of my CrossFit gym, or my then CrossFit gym in Leeds. The Environment Agency had a warning, but I was looking at the river gauges and mine was more precise. I didn't compute anything. You just do linear extrapolation. You look at every 15 minutes and you make a decision. People thought, I had 10 computers and calculated. Well, come on. Just look at the river gauge and you can make a decision. So I said, you better get there and let's get going. And this was at the end. At 6 o'clock, I was watching the river gauge all the time. I said, we have to go, otherwise we're locked in. It was this deep when we waited out. So I blocked out everyone, but this is me. That makes a big impression. It doesn't leave you. When they said later, the firefighters at the CrossFit gym, you shouldn't have been there. but we were. There was actually a firefighter amongst that group. So how well can we mitigate flooding? I appreciate that you might not know about the different mitigation measures. So which ones do we choose? We can hire flood defense walls. We can use floodplain storage. The little abbreviations, dynamic when you use weirs and optimal control. Giving room to the river. Natural flood management, and the flood is small because hitherto for the bigger floods, it's small. Nature value is big, flood mitigation value is small. That brings me into trouble often. Beaver colonies, it's the same size as floods, should even be smaller. Sustainable urban drainage systems, dredging, resilience. So now I just give you the pictorial overview, right? Because at this stage in the afternoon, you want to see pictures. This is a particularly nice wall, where I always think, well, how often do you need to clean it? But it is nice to clean it. I mean, how sustainable it is. In Leeds, you would need to have some of 2 meters high, which are not this nice, by the way. Giving room to the river is the following. You take a cross-section of the river and you decide to lower the banks so that they're normally not flooded, so you could use them for something else. You can even build there, as long as you don't block the volume. When you build spills, right? You see that along the Thames and so on and so forth. This effectively lowers the water height, and there's a quite nice kind of rule to visualize that. Another example of giving room to the river is at bends, which often calls storage. You can have an extra channel cut, which alleviates, can be low, dry in normal circumstances, but it gets active when the river is in flood. This is an example of the River Aire. In the River Aire, it has about 350 cubic meters per second in the flood. Another river is basically a branch of the River Rhine, essentially the River Rhine, then the numbers are a bit larger, probably around 15,000 cubic meters per second, just to give you that sense of scale. And this is a branch cut, it's in floods, which is normally blocked off and then used for recreation. But when the pressure becomes too high on the city of Nijmegen, this channel helps lower the actual river levels, but not by that much, but calculated to be just enough or to be helpful. This is a case of floodplain storage. This is the River Aire in Leeds, available. Normally this floods already, but by building a dam with movable weirs, you can bring it above its normal floodplain storage levels. This is an example. You don't know what the word weir means, which surprisingly people, I know that since the age of 6 because I'm mad at water. But basically you have gates in your river which you can operate so that you can block the water, actually lower to for example, to change navigation. When you live along the River Thames, you know about this. There's like lots of them. And you can use active control. You can also do it dramatically wrong. If you fill the floodplain by having it blocked, it's filled and you actually have negative floodplain storage, because that's worse than in the case without the dam. So you have to be very careful how you operate these. Another example is that you have overflow areas, just to give you a sense of size. This is one in the Netherlands, 20 million cubic meters. But remember, I mentioned 40,000 cubic meters per second. It's basically the same river. And then you build dikes to protect the locals here. Right? And you pay off the farmers for this function they give it. Another option is natural flood management. For example, leaky dams, which you put usually in the higher branches of the catchment, where normally the water flows under, but when it rises, this blocks the flows, and you need loads of them to make impact. It has extra benefits, nature value, because you get more wetlands, carbon sequestration, and so forth. Beavers. Loads of stuff. Oh, and I wouldn't have caught it. This is good research, what your researchers do, but it needs the word not. Definitely. It's minute. And the reason I spotted it, because they express the flood volume stored behind 13 dams, not as 1,100 cubic meters. But two ones and 5 zeros. So basically in terms of liters, and that why so many zeros? Now you wouldn't know if, because what does 1,100 mean? You first need to know what it means. And is this what's to prevent? Forget it. Sustainable drainage systems, usually they're very sexy with flowers and it's very nice. I totally agree with you. But I ran into this one, which is very innocuous, but it's maintainable if the council doesn't have enough money for a while, right? You can almost make machines which just take the cutting here. So you have to be a bit careful with the sets. I think they're sometimes too fancy, at least for poor councils. Dredging. I was invited by the Wainfleet Flood Action Group. They thought as a Dutch person, no, partially, that I knew about berms. I said, I don't know anything about berms, but I'm coming anyway if you wish. So I did. Here you hear about dredging. The person who led me around actually told me he built a new house, and the new rule of the council of Wainfleet is that houses need to be raised by 80 centimeters, so the first floor is higher. And that was calculated as then your house is safe, right? You might have to move your car if it's not high on an 80 centimeter level, but that's a good idea. It's an old idea. So this is an example of one in the floodplains of the Rhine River, bit high, right? So you could say this could be a sustainable.
Yes, a comment. This summer I took the boat from near Windsor, near the castle, and the guy in the boat told me if you go along the river. So the most new houses are about 1 or 2 meters above, and they said that the insurance is there. Don't pay for flood damages if the house doesn't have this sort of 2 meters gauge in the bottom. Yeah,
I think that's a great strategy.
yeah.
It's not that much money. There's not that much money. You can even build in floodplains as long as you do, and actually you should obey the zero-sum rule. If you take away volume from the floodplain, you have to give it back. And apparently, I didn't know this, I think it's already a rule, it's not always maintained, but the insurance companies are paying you money to maintain it. Okay, then what's the graphical cost effectiveness tool? So we go to the top left, A. Now what you need to do is first bend your head and look at quadrant 3. Quadrant 3, right? Bend your head. So what's usually, this is water level measurement along the river at the critical spot, at the relevant spot, water level, versus time going down. That's what's usually measured. But I want to actually top right, the first quadrant, discharge or cubic meters per second versus time, which is usually the measurements of that are less frequent. Sometimes they're in tandem every 15 minutes or every half hour, but usually there are fewer measurements of this. So then with those limited set of measurements, a rating curve is established. That's the blue line, which is a relationship, not always monotonic because there might be 2 branches, but on average 1-to-1 between water level and discharge. So now this 3-panel graph, I invented, or we invented, but nobody did this, and I thought, how is that possible? But anyway, I haven't seen, maybe Rebecca can comment, but that means if I pick a water level, I can go take the line up to the blue curve, and I go horizontal, and that gives me my value in the hydrograph, right? The graph which I like, right? I like graphical depiction, right? It makes it really clear. Now, let's take this line and say that's the threshold water level above which I get flooding, right? You determine that. Yeah? So I can go up and find the threshold discharge for which I get flooding. That means that this blue area is the flood excess volume. It's the volume which you want to remove to not have flooding for that effect. Right? I mean, it's an area, but since it's cubic meters per second and you integrate over time, it's a volume. Now you can display that as a square lake, conceptual lake. It might move, right? It's not necessarily less, but just, and in this case, it's 2160 meters by 2160 meters by 2 meters. Now, why did I choose 2 meters? First of all, because I'm 195, so it's pretty much 2 meters. More importantly, then everybody has a sense that they drown, right? You want that sense of fear. Of course, with 1 meter flowing, you're already dead, but 2 meters does the job for sure. This gives you 9.34 million cubic meters for this particular event. It's the Boxing Day event in Leeds. Now I have a sense of size. That big number is, well, big number, not a big number this guy comes up with, right? So now you can see whether this length, whether that fits in the catchment. Some catchments are very narrow. This catchment is 50 kilometers, 50 miles, and the river width is between 200 and 600 meters. So you think, well, probably should be some spots to do things there, right? For some river floods, it's hopeless. It's so narrow, run for the hills. You can't do anything because there is no place to do much. So what I can do now, first of all, this is exaggerated scale. 2 meters is pancake thin, probably thinner than this blue line, relative to its length of 2,000 meters. So what I can do first now, I can say I take 3 flood mitigation measures. That's why I needed to spread abbreviations. Higher walls, hard walls, giving room to the floodplain storage, and I carve up the volume which I want to reduce to 0, so that for that effect, I don't have flood damage. Now, since it's pancake thin, I can better make it a square leg pie, right? And look from above, because there's no point in the third direction, it's 2 meters. And now you can put in the cost per measure, the cost per percent by just defining the percentage which it covers, say for all 3, and then you can compare them readily, and you can put in the total cost. Well, that's it, it's the whole cartoon. And the civil engineers told me it's because you're an applied mathematician that this wasn't done before, because you came out of the blue. So now I'm going to show some examples. So it's the same graph, it's from the motivated by the Boxing Day flood. It turns out actually the level, critical level was 3.9 meters. And in reality, there is some uncertainty about this on these rating curves, which are slightly exaggerated. I probably did statistically what you shouldn't do. I took the worst case, just have a number. And this comes straight, this data from the Environment Agency. You can ask them. That also means if there's some fuzziness in the rating curve and you only have 15 minutes water level measurements, there will be some fuzziness in the flood excess volume. It lies between, it's about 16%, between 8.83 million and 9.86 million cubic meters. And this is a good one. We have ones with 50% in the spread. So these are, and this is how it started. I analyzed Leeds flood mitigation plans motivated by the flood evacuation. So I made my square or our square leg plots for one scenario, which has higher walls to 86%, giving room to the river again 7%, actually floodplain storage 7%. But I didn't stop here. The floodplain storage depends on how you do it. You can actually make it a bit larger, so you can use the vertical axis to put basically some uncertainty in. I can also add natural flood management, for which I got no numbers, but they said it's between 1 and 5%. And then the beavers, 1,100 cubic meters, 9.34 million cubic meters. You divide the two, you need about 88 or 8,500 beaver colonies. 400%, I give you that. That's too much. 10%, 850.
So you can measure flood risk in unit of
Beavers,
Sorry, the beaver is gonna become the
That's- No, but there's the people, I mean, I'm not, I mean, I make a joke out of it, but seriously, people say, well, that's flood protection for free. And that's assuming with no collateral damage, right? 1% is 85. I asked some nature organizations in the area, is there a place for 85 beaver colonies? And you can actually look up in here. I looked up the natural beaver density in
unit of flood risk.
no, there are serious articles about it. They're very good articles, but that gives you an indication of whether it fits. It just doesn't fit. And I asked the nature organization, 5, please, I want 5. Maybe. But in the graph, it's a sliver. So basically, it's for the bigger floods at the nonsense. Now, I thought I had one, which is small flood, but when the small flood, the catchment is smaller, so it's still no speed, right? To have a major contribution. I'm in favor of reintroducing, let me just be clear, right? Clear for the video. I'm in favor of introducing beaver colonies, but do it for their wildlife. Don't exaggerate, you mislead me. And it's just 2 numbers. I wouldn't have gotten on this if you hadn't called the meters with all those zeros. I mean, the zeros caught me. Now, for the Leeds flood mitigation plan, which is about 40 pages with loads of numbers, the first 3 summarize that whole plan in 3 graphs. And I thought that's much, maybe blow them up a bit, I thought it's much clearer. So you see that the green is a bit different, that squeezes the hard walls from 210 210 to 2 to 1.95 meters. And then we introduce a third one where we really have a bigger floodplain storage halfway upstream. And this one is the cheapest. This one without the beavers, with the natural flood management, and now it gets dangerous in a few slides. The beavers are not there. The floodplain storage 1 to 5% actually was pretty bang on, you know, which is so this is basically a quick way to play with it like Lego blocks and to see what happens. Of course, the decision makers need to read graphs, but I think decision makers should be able to read graphs, or otherwise they should be taught to read the graphs, right? I'll skip this one. You can, other people did it for the river Glen Sika, and I do want to make one point. When people make these flood mitigation scenarios, they pick a design flood against which they want to protect. So they express that as this is the 1 and 2 in a year return period flood. So that's how the two sections where Tropolis and this flood mitigation part link. So one can do this for a river in Slovenia. I don't want to go through it, but this is much smaller, right? It's just 0.3 million cubic meters. Gives you a sense of how this varies. It was done in France, and that relates to the last speakers because this was also in Maritime Alps. There was a flash flood. And I have a final link with your talk at the end. So you can, and they actually used it to negotiate and talk with the municipality in France. So the French engineers, Piton and Jean-Marc Tagné, they're actually co-authors, they used it. So this tool, in all its simplicity, with no intention a priori for doing that, was able to find inconsistencies in a public report. It showed that natural flood management is often overstated. And if you graph it, you see that the words don't match the numbers. And that's the curse of being a mathematician, I think. We like the numbers, right? So we get on that. It turns also out that they had 2 floodplain storage volumes in their report, which led to a novel concept, apparently, of available flood storage volume. You can ask me about it. And the location of the weirs was not optimal. That was in 2018. Now, in February this year, I asked for the data, not intending to do anything nasty, but just plot the data and do my cost effectiveness analysis. I thought, I have another example, I like examples. So I got finally, after 5 months of haggling, I got from a certain company, we claim that they can protect with natural flood management, they can get a 5% reduction of the extra at first water level heights due to climate change. So they sent me the report. Now, the plots are poor, but they're not mine. It's just their raw plots. It's Qmax, around 350 maximum. They took a baseline flood. It's very difficult to see, but the top one is the baseline simulation. It's the black line. And the other ones are all kinds of different flood mitigation methods. So if the claim is that there's a 5% reduction, then you draw, that's my line, the 95% line, and you need to stay below. Now here's the difference plot. That's why I could go through the appendix so quickly. And indeed, where the maximum is, this is around 17.5, which is indeed about 5% of 350, right? So I could quickly link to the report. I was looking for those. But the problem is that that's this red line here. But the red line here in the first peak is pretty much at the top. In other words, it's still flat. So I talked with several people and I go, maybe I'm daft, right? But maybe I am daft anyway. But the point is, well, what's going on? Well, it was lukewarm, so I sensed this out. There's this sense/sensor in latex. I sent it out. It was lukewarm, the response. That's put in a friendly way. There was a limited time for peer review. Oh well. But what the company asked is investments of 4.25 million. And I'm not sure whether they are aware that there is only 2.5% reduction in that report. I think the missing 2.5% comes from land management, including soil erosion, which was presented in February. And for that one, I asked the evidence. And either they don't want to give me the evidence, or I think they added it, but don't have the evidence. Because I haven't seen it. And I must say, both soil erosion and land management are not NFM, so the whole measure is not NFM. So things like that has worried me for a while. So last year I was writing an invited article, and they told me read Morgan and Henry, which is from 1990. It's 1.5 generation ago. So these quotes just set me straight. I thought, oh, this is something which happens through human life. So it said, I just quote, this means, however, that peer review should be more uniformly extended to policy-focused research and analysis than it has been in the past. So this was a problem for the review as well, which is good because you feel like you're among peers. It's bad because it should be there, right? Then they said, well, there should be institutions and traditions that protect experts who participate in elicitation. Mine wasn't non-requested one, but nonetheless, from entanglements. And then somebody had said an excellent example by partial anonymity. But I don't like partial anonymity because our institutions ask refs an impact, right? And my co-authors wouldn't have worked with me. I said, well, my name goes off and I take a fake name, right? So there's a bit of a stress there. So I have discussed the matters and I hope they get fixed. But the lack of scrutiny should be a point of wider discussion. If a paper of mine that has been very recently, somebody finds a bug, I withdraw it and I fix it, right? I mean, it's a matter of standard. I mean, you have to do that. You curse. I'm not saying you should curse, but you do it. So I'm at the end. I have a little slide more, but I leave it to. I come to the end. So this analysis is actually 0D in space, but it actually applies to a stretch of river, and there's some fluid dynamic thinking here. You can, I haven't done that, but you can include ensemble forecasts if you want to have more uncertainty. But this cost effectiveness approach is an essential input in the whole chain. So it's not by itself a proper safety and reliability approach. You do want, if you have the money and the time, the full engineering simulations, but you would like something like this, mine or something better, ours or something better, as part of the whole chain. Not in the least, because apparently, in all its simplicity, it's able to find inconsistencies and errors, to my surprise. So this part, I should really thank Jean-Marc Ternay, because he, as a civil engineer, is much more well-versed to deal with these matters. So he insisted, you need to say this, because some people think that what you made is a method, but it's a diagnostic. I mean, I saw PDs and ODs as well, and I'm not doing that here. I take other people's data. Now, how further? I'm busy with creating Metropolis World and use Metropolis as a laboratory and scientific setup with a matching numerical Metropolis model, NWP, pun intended. One of the Metropolis World's goals is to investigate classical partial differential equation and data simulation methods, numerical Metropolis prediction methods with machine learning predictions. So Professor Stephen Belcher, the director of the Met Office, gave a marvelous presentation, which he probably has given more often, where he describes how there's a camp in the Met Office which wants machine learning exclusively, a camp, I'm exaggerating slightly, only the classical way, and then somewhere in the middle of both. So running a real numerical weather prediction model is too much for me, but I think in the Metropolis world, you can actually look at this entire discussion, including the ability whether such models can deal with extreme events beyond the data set. But I manipulate my own data set, right? So it's nice because I can create things and much more easily in Metropolis, and I have errors in it, which just naturally emerge because it's a laboratory setup as well. Now, I was pleased, so that's probably for Nick, outreach gets very little funding. I wouldn't have done Metropolis if I wasn't to right? There's just no time for it. But now the APRCC Fellowship Plus, the plus, I fell off my chair. The first time I've seen a fellowship where you can have 20 to 50% of your time dedicated to outreach and education. And when I saw it, I said, that's me. So I end with that cry, that's me, and I aim to put in a proposal. Several papers which supported all with 9 authors I commented back out with latest research, but rather because I was so impressed by your 140. Mind you, there are lots of undergraduate student projects on this, and all the stuff is online. The design is in the GitHub online. The graphical cost effectiveness tool, you can't do it yourself. R, MATLAB, heights and codes, everything is online. Everything is actually open. So that's it for me. Thank you very much.
Thank you for this excellent talk. Do we have any questions?
How, for the outreach and educational purposes, how important do you think having the Gaussian board is as opposed to having the numbers generated by a computer? If I understand how it's being used.
Yeah. So
It's important for people to see the ball rolling or
at least enough because it dominates. Yeah.
Like a pinball machine.
That's what it's like.
So I actually want to make a 1/4 version, but then and then not to make money, but it may have to make money, but that's not what it's about. But then you may need to make it more robust, and I think you need to do less. But with lights and sound, you can add sound, you can probably get pretty close. Oh, I didn't say that, but it's also the intention to make a board game, so I bought 2 16-face dices. Other dices, and now I can get back to you. People say I need to add sewage because of the sewage in the board game, brown chips, right? But the interesting thing with sewage is when you have a sewage spill, it's usually very short. The water's clear, and then some water company comes in and says, well, it's clear. But the interesting thing is like the canaries in the mine, I learned this from other people, what you have in the river are viviflies, and the viviflies population gets wiped out much longer than the event, so you can use the vivifly count. So I have something to say finally. You can use the vivifly count to find out whether there were spills, because they take I don't know, a few weeks or something. The spill is usually a couple of hours. So that has been used in lawsuits against a particular water company.
But the famous one with the thing, the one with the name starting.
No, IMA.
Okay.
So I work with people in Bradford, friends of Bradford's back, and they know all this stuff. Right? Just a Dragonfly story is really interesting story.
Yes, any more questions? Yes,
Did you check statistically whether your bulletin boards actually give the probabilities that you?
Yeah.
So I'm just.
You saw a little screen on there. Yeah, we can do the check. It's not perfect. So in one of the first ones, we just did the hand count. It's not perfect half split, and sometimes the stupid ball they hand, you need to wait for the second ball to kick it off.
Yeah, because I think Gaussian boards are extremely sensitive to any imperfections, which is not, I mean, doesn't invalidate.
I mean, for the demo, I don't care.
No, you don't care. Of course you don't.
And people said your system is chaotic. I said, well, strictly speaking, in the ideal limit of simulating the rainfall, it's not. I just probabilistic statistics, but there's no chaos in it. But in real life, it's probably chaotic because you get these disturbances, noise on the splits half.
But you can make the point that, the numbers you put are already some sort of simplification, while reality is just this ball, right? And
Because why don't worry.
Yeah,
That's fine.
Exactly.
It's fine.
But and so these bulletin boards, they are very sensitive, for instance, to tilting and.
Oh, I know. I'm with whenever I go somewhere with my, because it's actually a portable setup, so I could have brought it, and sometimes I bring it, like at the Mathematics of Planet Earth, where I'm running for 9 days, and then you have to fix sometimes a thing or two, right? So it's not yet machine proof.
There's another, I remember this discussion also when you were running with it. there is some sort of climate change, and that there was some significant evaporation, no? Have you done something about that, or?
So that's correct. So halfway the day you see that because there's a reservoir underneath. I can go on for hours. So the setup folds in two. And it leaks like mad. Not on the ground because I have a gutter. The first one was from home base, where it's slightly sexy one. And it leaks back into aquifer because in real life, rain was also disappeared. So that was me saved by the bushing, but aquifer, but it should be circulated. Evaporation, just look what the level is in the reservoir aquifer and just delete it. It surprised me after dates significance. You have to be fit. Yeah. But I wouldn't call it climate change, just evaporation. Because there's so much wetted surface, so you probably calculate it.
Good. So I think in the interest of time, we will end here. So let's thank we have now a half an hour coffee break, and then we'll have a panel.